In this section, we're going to go over something called the least square regression line, and this is often used to make predictions. So to begin, I want us to remember the equation of a line. So this should be reviewed, but just in case you forgot, the linear equation is an equation of the form y equals mx plus b, and its graph is a line. To graph this equation, start by graphing the point that results when x equals 0, or your y-intercept. So b is your y-intercept. The variable m is the slope of the line that represents the rise over run. So here m is your slope, and it's just rise over run. So, okay. So for example, let's graph the following equations. So here we have y equals 3 over 2x minus 2. So your slope, m, is 3 over 2, and your y-intercept is equal to negative 2. So if you label this, so let's make this 1, 1, 2, negative 1, negative 2, 1, 2, negative 1, negative 2. First thing you want to do is mark your y-intercept. So this is your y-axis. So here we have negative 2 right here. So let's make a point right here. Since your slope is 3 over 2, which is equal to rise over run, we go up 3 and to the right 2. So you go 1, 2, 3, and then 1, 2. So this will be another point of the line. Since you already have 2 points, you could connect them, and that will be the line of that equation. Actually, let me do this. Fantastic. So here, this line is represented by this equation. So how about this one? So here our slope m is going to be equal to negative 2. And you could think about this like negative 2 over 1. So this is like rise over run. And then your y-intercept is equal to positive 1. So here, like this, 1, 2, negative 1, negative 2, 1, 2, negative 1, negative 2. First thing you want to identify is your y-intercept, which is 1. So you go 1 here. And your slope is negative 2, or negative 2 over 1. So that means since this is a negative, you go down 2, 1, 2, and to the right 1, 1. So here's a point. And since you already have 2 points, you could connect them and make a line. Sweet. So this is how you make a line using y equals mx plus b. So this is going to help us when we discuss about the least square regression line. So here, some important definition. Suppose you have 2 variables and you detect some correlation between them. Studying the effect of one variable on another is called a simple regression. We will call the variable we choose as x the explanatory variable, and the variable y to be the response variable. In simple linear regression, we will study the effect of the explanatory variable on the response variable. We can also use this to make predictions about the response variable. So for example, this is the same data of sizes of houses in square feet and their price value in thousands of dollars. So notice that I can make a line. I can make a line here that could correlate with these 2 variables, like this. But notice that, how do I know this is the best line to choose? So what if I make what if I make a line that looks like this? So notice that it's kind of, it doesn't fit the data set as well as what I wrote here. And how do I know that? If I take the distance between each data set to that line, I'm going to have a lot more error than if I did it here. So the question kind of forms that, what is the best line to fit a data set? And that's something that we're going to discuss. We call it the least square regression line. It's also known as the best fit line. So those are the two common names for what we're going to do. The reason why it's called the best fit line, because it's literally trying to get the best fit line of the data set that we're working with. Okay, so the least square regression line. So the regression line, or the line of best fit, the least square regression line, they're all the same thing, is the line that best fits the scatter plot of our data. The equation that we are going to use for the line of best fit is y hat equals b1x plus b naught, where b1 and b naught, or b0, they're values, they're like numbers. And that's the idea here. We're trying to find a line that's the best of a data set. So how do I get these values? How do I get these b1 and b naught? Well, this is how we compute it. So given ordered pairs x and y with sample mean x bar and y bar, and sample standard deviation sx and sy. So again, sx, sy, they're just the sample standard deviation of our x values, and this is the sample standard deviation of our y values. And then we have to have the correlation coefficient r. The equation of the least square regression line for predicting y from x is this, where b1 is r times sy over sx, and the slope b naught this is the slope, and this is the y-intercept. Yeah, so b naught will be y bar minus b1 times x bar. Since we calculated b1 here, we just plug in the values. And you probably guessed it here, but computing this by hand is actually really tedious. That's why we're actually going to use technology. We're going to use Excel to compute this. And you're going to figure out it's not that difficult to compute our least square regression line in Excel. All we have to do is just use some functions. So here's a step-by-step of how to compute our least square regression line. Y hat equals b1x plus b naught. We're going to use the standard deviation function, the correlation function, and the average function. So let me do a quick example. So we're going to revisit this example about the size of houses and our selling price. So let me just go to Excel real quick. So I open up a new Excel sheet and notice that I already inputting our data set. Again, this is X value will be the size of the houses, and then the Y value will be the selling price of each houses. I also made the scatter plot already right here. So the goal is to compute our least square regression line. So we need to compute B1 and B naught, B0. And to do this, we need the following result. We need to compute Sx, Sy. We also need Y bar and X bar according to our formula. Oh, we also need the coefficient, correlation coefficient R. Okay, so how do we find these values? Well, Sx is just the sample standard deviation of our X values. And in this case, it will be the size of the house in square feet. So to compute this will be equal to, notice here we need to use this function called stdev. So this is just the sample standard deviation. And we need to have an array, so to be this, and I need to close it. So if I do this, this gives me the sample standard deviation of sizes of the house. So for y, it'll be the same thing. We're going to use the same function, stdev, highlight all this, close it, and that will be our value. Next, we want to find our y bar and x bar. So this will be, we're going to use something called the average function. So it'll be y bar, so it'll be the selling price here. Close this. And then x bar will be all of this. So this is the average size of square feet, and this will be the average selling price of the house. Next, we want to find the correlation coefficient. And here, again, we're going to use the function correl. So it'll be x values and y values. And we already did some practice computing this in the previous section. So this is 0.9005918, which we did, which is the same value that we did in the previous section. Okay, now we want to compute our slope and our y-intercept. Yeah. So if you look back of our notes, let me just go back here. If you look back here, our slope, B1, is just R times SY over SX. And our y-intercept is Y bar minus B1 times X bar. So since we have all these values, we could just compute it. So here, back to Excel, this is going to be equal to R. So this is the value of R. Let me just put parentheses. So this will be R. So this is the value R times. So I'm doing the math here. Times SY, this value, divided by SX, which is this value. So if I press enter, this should give me B1. And it does. This is our B1 value. This is our slope. So our y-intercept, B0, if you look back of our notes, B0 is just Y bar minus B1 times X bar. So back to Excel, this is going to be equal to Y bar, which is right here, minus B1, which is this, times X bar, which is this. And if we press enter, this should be our y-intercept. So now we have our slope, and now we have our intercept. So this is all we need to compute the equation of a line. So this is all we need to compute the least square regression line. Okay, so let's go back to our notes. Going back to here, again, we want to construct the least square regression line. So this is asking, we want to find y hat is equal to b1x plus b naught. And we already found b1 and b2 in Excel, so we could just plug them in. So our equation y hat is going to be equal to 0.0992 x plus 160.1939. So this is our least square regression line. So what this means is that if we plot this line into our data here, we're going to actually make the best fit line, the one with the least amount of error. Cool. So this is important because with this equation, we can actually make some predictions. Okay, so some predictions. We can use the line of best fit to predict the value of the response variable if we are given some value for the explanatory variable. So what this means is that if you give me an x value, I will give you a y hat value back. So first, find the equation for the line of best fit, then plug in your given value of x to find y hat. If the given value of x is inside the range of the dataset, then the predicted value y hat was found by interpolating. If the given value of x is not inside the range of the dataset, then the predicted value y hat was found by extrapolating. Note, predictions found through extrapolating is not as reliable. The reason why is because since it's outside of your dataset, it can't be that reliable because, well, you're outside of your dataset. Let's do a couple examples. Use the least square regression line computed in the previous example to predict the selling price of a house that is the size of 2,800 square feet. So if you remember, we computed the least square regression line. So this will be y hat is equal to 0.0992x plus 160.1939. So we have this equation. So it's asking to predict the selling price of the house if we had a size of 2,800 square feet. And remember, this equation was corresponding to this data set where x is the size of the house and y is the selling price. So here we plug in 2,800 into x. Y hat is equal to 0.0992 times 2,800 plus 160.1939. And if you put this in your calculator, this should be equal to 437.9539. But let's just round to first decimal places. So this will be equal to 438. So in words, we could say that we predict that the selling price of the house will be $438,000. And again, remember, this is in thousands of dollars. So we predict the selling price of the house will be $438,000 if the size of the house was 2,800 square feet. Great. Let's do one more example. Use the least square regression line to compute the previous example to estimate the average price of all the houses whose size is 3,000 square feet. So here we do the same thing, or we do something very similar. Since we know our regression line, y hat is equal to 0.0992 x plus 160.1939. All we have to do is plug 3,000 square feet into our x value. So this will be y hat is equal to 0.0992 times 3,000 plus 160.1939. And if you put this in your calculator, this should be equal to 457.8 if we round to one decimal places. So in words, we could say that we estimate the average price for a house of 3,000 square feet to be $457,800, because again, this is measured in thousands of dollars.